Thank you for the opportunity to talk to you today about the Sargasso Sea and the Bermuda Atlantic Time Series program and some of the biogeochemical responses that we've seen over the last 2 decades. My name is Mike Lomas. I am a senior scientist at Bigelow Laboratory for Ocean Sciences and a co-PI in the BATS program. Both the BATS and OceanSITES programs were started with the goal of having and generating long-term, high-quality records of ocean variables. Now, the frequency of measurement varies between the two. The scope and scale of measurements and parameters measured differs between the two, but the overall goal is the same. And so I want to hop right into the Sargasso Sea and present to you some of the biogeochemical data that we're seeing there. So here I show the annual mean weighted temperatures in the top panel and the annual mean net primary production in the bottom panel. In each panel, you'll see a colored box. Those colored box boundaries define significant periods of significant trend in the data. So in the 1990s, we have a significant increase in temperature, and again in the 2010s, a significant increase in temperature. When we look at net primary production, in that same 1990s time frame, we see a positive increase in net primary production. But in the 2010s, we see a significant decline in net primary production. This decline in the 2010s is about a 35% reduction in the net primary production. So what are the biological and chemical processes underlying these different responses? Let's start with the physical forcing. The dominant physical forcing mode for climate is the North Atlantic Oscillation. The North Atlantic Oscillation comes in two modes. The positive mode leads to storms tracking a bit further to the north and leads to less mixing in the Sargasso Sea. NAO negative modes lead to storms tracking a bit further south and more mixing in the Sargasso Sea. In this bottom graph, we have the 5-year running average of the wintertime NAO values in the black line. Our two periods of interest are outlined in red. And you can see in the 1990s, our time period starts with a high positive value of the NAO that then declines through the time window. And in contrast, in the 2010s, we have values that are starting out actually slightly negative and then rapidly increasing positive through that time window. So this will impact vertical mixing and therefore nutrient inputs. So let's start with the vertical mixing. So vertical mixed layer variability, this top graph, we have the cruise to cruise variance in mixed layer depth. The middle panel, we have the annual averaged mixed layer depth, and the bottom panel is the wintertime, the January, February, March average mixed layer depth. And again, our time periods of interest outlined in red. The year-over-year variance in the 1990s was much more stochastic, whether looking at the annual values or the wintertime values, than in the 2010s, where the year-to-year variance was much lower, and in fact, on an annual basis, suggested perhaps that annual mixed layer depth was actually shoaling. So these two very different physical patterns have important ramifications for nutrients inputs. So let's look to the nutrient fields. So here we have in the top panel our temperature plot. In the middle we have our high sensitivity phosphate, and in the bottom we have our traditional autoanalyzer nitrate. And you can see that in the 2010s we don't have that deep mixing in the winter, and therefore the traditional cold period between warm summers tends to go away. It's clearly consistent in the 1990s. When we look at high sensitivity phosphate, unfortunately we don't have data for the 1990s, but in the 2010s, we can see the high values during the very early part of the time window where the NAO was negative. Once it rapidly became positive, you can see that the nutrients were very quickly mined from and to a greater depth from the euphotic zone. We see the same pattern in the 2010s for nitrate. But interestingly, when we look at nitrate from the 1990s, when net primary production was increasing, temperature was increasing, we don't see a similar pattern in the nitrate. If we take and plot those as the actual inventory values over time, the 0 to 160 meter integrated nutrient inventories, We can see that again for nitrates. There is no decrease in the nitrate inventory in the 1990s, but in the 2010s, phosphate and nitrate inventories very quickly decline from high values down to almost zero values. These result in a greater than 80% drawdown on average of the nutrient inventory. And interestingly, the ratio of the drawdown was about 37 to 1, which is a different biological story, but equally interesting. So the annual NPP could have dropped by over 80%, but in fact it didn't. And I would argue that due to intense recycling, it only dropped by 35%. So what's the data to support that? So let's start with the phytoplankton community in total. So given the time, I'm only going to present data for chlorophyll A, but here we have a time series of chlorophyll A, and for the more recent time period, our phytoplankton carbon biomass time series. So in the 1990s, you can see that chlorophyll stayed consistent in terms of its absolute magnitude as well as the depth at which that maximum occurred. Whereas in the 2010s, you can see very high values at the beginning, again, due to the enhanced vertical inputs of nutrients, but then it very quickly declined, and actually, interestingly, the depth of that maximum got deeper with time. When we look at the phytoplankton carbon biomass record, again, we see the elevated values at the beginning of the time period, but we don't see that same decline in magnitude. It just drops right off and stays stable after that, and it doesn't get deeper over time, suggesting that perhaps there are changes in the mean euphotic zone carbon to chlorophyll ratio through time, through this 2010 time window, which would be consistent with increased stratification and a change in the light environment that the phytoplankton are getting accustomed to. So what does this then mean for changes in the suspended particulate matter sitting in the Sargasso Sea euphotic zone? The top panel is our section plot of particle organic carbon. The middle one is particle organic phosphorus, and the bottom one is the sestonic C to P ratio. And so when we look at the 1990s, you can see that POC is definitely not decreasing, and perhaps one could argue it's increasing. Unfortunately, we don't have a complete record for POP, and which makes the long-term trends in that decade difficult to assess. But our C to P ratios tend to be closer to 150 or so. When we look at 2010, we can see that again, we start high and get substantially lower for POC. POP shows a similar pattern, but now our carbon to phosphorus ratios are more consistently getting to much higher values, often up to 300 or perhaps even up to 400. And this is consistent with the system responding to that decrease in phosphate inventory. So what does that then mean for carbon export and the sort of that functioning of the euphotic zone ecosystem at bats? So here we have plots of carbon flux in the top, phosphorus flux in the middle, and the ratio of carbon to phosphorus flux in the bottom. During the first time period, the 1990s, carbon flux is stable despite increasing net primary production and increasing temperature. When we look at the 2010s, you can again see that carbon flux is stable through this whole period, but the phosphorus flux, which started out high, actually decreases dramatically, again consistent with the reduction in the inventory. And the ratio then of the carbon to phosphorus, that's material that's exported, goes up exponentially. And in fact, if you look at the magnitude of the numbers, these values are now a factor of 2, maybe a factor of 3 higher than the suspended POC to POP ratio. So just quickly to summarize, there's a 35% decline in net primary production despite an 80% decline in nutrient inventories. And I would argue the ecosystem is adapting to mitigate these reductions in physical nutrient inputs through changes in the phytoplankton community and/or their physiology, leading to increased seston P use efficiency and further retention of P by intense recycling as those particles are exported. These physiological and biological responses are able to mitigate roughly half of the expected decline in net primary production with a minimal impact on carbon export, which is very important. And this suggests that the biology changes the NPP to POC export relationships in the counterintuitive direction of actually being more efficient with time, or with reduction in the NPP. So why does this matter? A recent publication has shown that while the Sargasso Sea is known to have very low phosphorus concentrations, there are other portions, particularly the Western Pacific, that also have very, very low phosphorus concentrations. Interestingly, the Western Pacific tends to have more OceanSITES assets than the BATS time series area does. And so perhaps we can take our knowledge of the biogeochemistry from bats and apply it to a similar ecosystem in the Western Pacific. And so with that, I will leave my acknowledgements and I will take any questions. Thank you.